I promised you last class that we were going to make HEMAbot's eyes light up. You can see I've got a new head on him that just looks a little bit more robotic. So we're going to get around his blade here and pull off his head. And we're going to go inside and see if we can make those eyeballs light up. To light up his eyes, I think what I want to show you the way that we're going to hook up our circuit is I got this snap circuit set right here. And let's just actually build a quick light circuit and see what that looks like. So in the snap circuit set, we can have this piece there where we can lay stuff out. Now to provide the voltage to actually power up his light bulbs, we need a battery pack. So we'll grab that and we'll just place that on here. And then we need a light bulb. So here's a lamp right here. So that could be one of HEMAbot's eyes. And now, in order for things to flow, for current to flow, there actually has to be a circuit. So we actually need electrons to flow out of the negative side through the light bulb and then back to the positive side of the battery. Okay, or fancy terminology, we need from the cathode of the battery, we need a conductor taking us to our load, which is the light bulb, and from the other side of the load to the anode of the battery. So basically, in a nutshell, what we need to do is we just need to wire it up. So I'm just going to grab a couple of these and we just kind of snap them in place. And we see, hey, there we are. So there's a light bulb that's lighting up because we have closed the circuit. It is a closed loop. We call that a closed circuit. And that's something important to point out is that an open circuit is when we actually break the circuit. Okay, so we close the circuit to turn the light on and open the circuit to turn the light off. And that might sound backwards for some people coming from some languages where you talk about opening the light and closing the light. But closing the circuit actually turns on the light, and opening the circuit turns off the light. So in a way, it's the opposite of a water tap. So I just wanted to clarify that. Okay, but we can hook up a light here. And that looks like it would look really nice on HEMAbot's head. So we can take this right off of HEMAbot here. This mask part just comes right off of him. And we can put the... Let's just see how that would light up behind his eyes there. Oh, that'll look pretty cool. So we can do that, but we actually want to have two light bulbs, right? We don't just want him to have one light up eye. It's not like we're going to put a patch over the other eye and he's a pirate. Although that would maybe be a good advertisement for wearing safety gear when fencing. But what we want to do is hook up another light bulb. And there's basically two ways we can hook up a light bulb, in parallel or in series. And we want to hook our light bulb up in parallel because that actually gives us more control over how much current we have going through the bulb. And we'll see that as we lurk along. But let me just add another circuit in parallel. So the issue with this light bulb right now, the way it's hooked up, you can see is that there's one path for electricity to follow all around like that. Now, when we're making a parallel circuit, it means it branches off. And we can create a whole other path for the electricity to flow through. So I'm just going to rewire that now. So put another light bulb in place, but it's not connected yet. So if I want to connect it, I need to add another wire on this side. But I also need to put another wire on the other side. And there we can see they're both lighting up. And that would make HEMAbot have some really nice light up eyes there. Oh, can't quite put them in place where they are. But we can see, I think that'll be a good look for HEMAbot. What do you think? So the way I hook this up is that it now branches. So as the electrons are coming out of the negative, they've kind of got two paths that they can follow. And they can take this path, or they can take that path. Now, the distance doesn't really matter to the electrons. What matters is the resistance from both paths. And here's the thing. We can think of these wires as being like a superhighway of traffic where tons and tons and tons of current can flow through them. So if I have that unhooked, what's really slowing down the traffic is the light bulb. It's like we have a superhighway leading onto a back lane. This is the bottleneck. This is where that traffic is really going to get slowed down. Now, if I hook up another path like here, I've got superhighway, and I've got 2 back lanes. So what have we basically done is we've said, hey, I've got 2 ways I can really feed that electricity and let it go through now. So coming off the superhighway, we've got 2 paths that can be followed. So we're going to get twice as much traffic coming down this superhighway because it's really only these back lanes that are holding it up. So we're going to get twice as much current coming out of the battery. This light bulb is going to have the same amount of current whether or not that other light bulb is held up or not, because this is where traffic is backing up. If I make a whole other path for that electricity to follow, it doesn't really affect this one. It's still doing what it's doing. It's still taking all the traffic it can, but so is this now. So what ends up happening in a parallel circuit is that each branch on a parallel circuit doesn't affect the other branch in a perfect world. In the real world, there's sometimes some limits what batteries can do, and they have something called internal resistance. So in the real world, maybe they will a little bit. But in the perfect theoretical world, no branch of a parallel circuit is going to affect another branch. Okay? So the only time when we really have to worry about one branch affecting another branch is if one of them is a short circuit. Like I do that. Oh, notice they both turned off there because all of a sudden, why would anybody ever take these back lanes if they're superhighway all the way? So if I touch this, everything goes out there. I don't want you to ever do that. That's called a short circuit. If I left that hooked up and those bulbs turned off, it's going to make my batteries go dead very quickly. It's also going to make all the metal in these wires get really, really hot because we have a lot of stuff going through them. And there's a chance the batteries might burst. So there's a whole bunch of bad reasons why we don't ever want to do that for longer than a split second. Okay? So we don't ever want one of our parallel circuits to be a short circuit. A short circuit means there's a path there we didn't intend, and we don't want that. So that's, in a nutshell, the idea of the circuit we want to build. So let's just talk a little bit about numbers when building for HEMAbot here. Let's look at some example questions. So I've shared a question sheet with you with all sorts of questions that we're going to learn as we're going through with HEMAbot here. But I want us to look at this first one right here. If a 9-volt battery is hooked up to a 3-ohm light bulb, what amount of current will flow through the bulb? And we want to use Ohm's law for doing that. So just a reminder, Ohm's law is I equals V over R. And here on the worksheet, I did give you the formula triangle for that. So this is basically all 3 forms of that triangle so that you don't have to do algebra. You just basically cover the one that you don't know that you're solving for, and it'll give you the equation for how you get that. So we'll see how that works in just a second, but we're going to look at this first question about the 9-volt battery, a 3-ohm light bulb, and solving for current. I always suggest when you're doing an electricity question that you underline the important information and then say what it is. So 9-volt battery, that's potential difference or voltage. That's the letter V we used to represent that. 3-ohm light bulb, that is R for resistance. And we're solving for current, that is I, represents the concept of current. So we have I, V, and R, and then we find a formula that fits the bill. Now, of course, in this training page, I've actually shown you they're all paired up already with the right formula, so you don't have to think about it too much. But we have I, V, and R here. So we cover up the one we don't know. We're solving for I. So what is I? V over R. So I equals V over R. So I write the formula in that format. I actually already have written that. And then we plug in what we know. So V is voltage. Do we know voltage? Well, yes. The question says it's a 9-volt battery. So that's 9. And I ask myself, is that the standard unit? Are volts the standard unit for potential difference? Yes, they are. Because if they're not, we will want to convert. But we don't need to worry about that right now. So R is 3 ohms. Is ohms the standard unit for resistance? Yes, it is. So we can just plug in the number. And we know that if we're all using standard units, our answer is going to come out as a standard unit. So 9 divided by 3 is 3. And that's not our final answer, though, because we need units. So we're talking about current. And the standard unit of current is the amp. And because we use standard units and standard units, we get the standard unit. So our answer is 3 amps. And that's generally a good amount for a small light bulb, like the ones we just used in HEMA's head. So HEMAbot's head is going to light up really nicely with a light bulb with 3 amps in it. So that would be a good light bulb to include for him. The second question is done very similar to the first. So what we usually want to do is identify first what are the important parts of the question. So as I read through this question, kind of mentally underline these yourself as you see the important words here. What voltage is required to create a current of 0.5 amps across a 200 ohm load? So what is the important information here? Well, what is it giving us? It's telling us that there is a current of 0.5 amps. So what is current? Current is I. So we have 0.5 amps for I. It's telling us we have a 200 ohm load. That's a measurement of resistance. So we know that resistance is 200 ohms. And then what are we solving for? We're solving for voltage. So the 3 letters we're looking for, I, V, and R. And of course, because we're still learning, you know that's the formula that you're using. However, in this case, we're not solving for I like we were in the last question. We're solving for voltage. V is the one that we don't know. So we cover up the V. Oh, it's I times R. All right then. So let's plug in then. So V equals I times R, which is I is 0.5 amps. Amp is an SI unit. Beautiful. I don't need to convert. Resistance is 200 ohms. So that's also an SI unit. I don't need to convert. And so 0.5 times 200, or 1/2 times 200, or half of 100 is obviously 100. And then we need the unit. What is the unit for potential difference or voltage? It is volts. 100 volts. So that's the second question. Okay, the third question about Ohm's law. What resistance would cause a 120 volt appliance, which is very standard for a home appliance to have 120 volts peak voltage. So what resistance would cause a 120 volt appliance to have a current, oh, there's a keyword, of 0.4 amps. So what do we need to know? What do we know? Well, R is what we're solving for. That's the thing we don't know. That's the thing we're going to cover up in our formula. We do know that voltage equals 120 volts, and we know that current is 0.4 amps. As I get better in this, I don't necessarily write out every line of what I have. I just kind of make a little note of exactly where I'm looking and what letter I'm going to plug in. So I've got V, I, and R. I'm covering up R in my equation. So R equals V over I is the format that I want there. Okay, so we can plug those in. So that's 120 divided by 0.4, or 4/10, right? So 120 divided by 4 would be 30. But keep in mind that when we're dividing by 1/10, it's actually going to make our answer 10 times bigger, right? Because we're dividing by 4/10. So that's going to give us 300. And that'll kind of make sense if we remember this is about a half. About how many halves would it take to make 120? Well, it would take about 240, or exactly 300 in this case, right? So 300, but 300 what? What is our units? Our unit of resistance is the ohm. So it's 300 ohms, right? If we have SI units and SI units, we get an SI unit out as our answer. So the answer for that is 300 ohms.